it's great to have opportunity to finally talk in front of people that are here. So I would like to thank Alex and Frédéric for organizing this event, and it was very pleasant so far. So yeah, I'm well, almost new in Paris here. I joined a Leipzig group 2.5 months ago. So, and it's good to be here. So yeah, my title is about self-testing, as Frédéric said. So the title is Quantum Networks Self-Test All Entangled States. So well, it is a manuscript that is not yet published, but it's in preparation, and I think it will soon be on archive. So it is done in collaboration with colleagues from Barcelona, from ICFO. So that was my group where I did my PhD. So Joe Bowles, Marc-Olivier Hanou, Antonio Assin, and Matti Hoban from Goldsmiths in London. Okay, so some contents before I start to give an overview about what will I tell you. So well, I didn't say, but you are free to interrupt me whenever you want to ask a question. It's fine by me. And well, also I think that 1 hour is quite a lot of time. So okay, so well, we'll start with a bit of philosophical introduction about how do we learn things, or what is the process of learning or understanding. Then we'll move a bit to Bell monolocality, that is the core of self-testing, which I will introduce in a bit of gentle way, right, because I have time. Then I will have some intermezzo about certifying through quantum teleportation, and then we come to the main result, that is how networks aid self-testing, or you'll see how I will later call it, how we can create something called teleportation-assisted self-testing. And I will end with the 2 open questions that are, in my opinion, important for this. Okay, so we start, as I said, with some philosophy. So we have this very famous guy that was one philosopher that introduced something called methodological doubt. And well, arguably, this was the time when philosophy was somehow paving the way for really creation of scientific method. So Descartes was asking, well, how do we know that things exist? How do I know that I exist? So simple answer would be that, yeah, I see things, I see all of you, but what if I cannot trust my senses? What if there is some demon that is making me believe that I see, that I smell, that I touch, but nothing of that exists? So this methodological doubt was a very good tool towards finding answer on a question, okay, how do we know that something exists instead of that nothing exists? This big question that already Greeks were posing. So well, his answer was, je pense donc je suis. So I think thus I am. And then, so the question that we get out of this is, okay, can we really trust our senses? So in some sense, like, well, coming closer, I will soon come to theorem of physics, but that is already there. So our senses are all the time making some measurements, that when I see, when I smell, I'm making measurements. But okay, indeed, like the question is, like this philosophical question was, how much can we trust this? And well, by asking this question, by posing this methodological doubt, like, well, Descartes made a significant contribution to philosophy. And then, well, how is this all related to quantum information? Well, I mean, first thing is that, well, we know that one field for development of quantum information, one big field was cryptographic scenarios. So there we many times take into account that there is some adversary that might be corrupting our measurements or our sources, or well, all our lab, basically, I don't know. So somehow this Cartesian methodological doubt finds its analog in modern quantum information theory. So there, like, as I said, there are Alice and Bob. In some cryptographic protocol, they have this methodological or systematic doubt that evil eavesdropper Eve might be intercepting their communication, stealing information. And yeah, so this doubt goes so far that Alice and Bob don't even want to trust the devices they are using. And then the question is, okay, is it possible to gain any knowledge? Is it possible to make communication secure even if you don't trust the measurements? So, well, in classical physics, well, it requires trust. So somehow gaining any knowledge requires perfectly characterized measurements. So if we don't trust our eyesight, well, we will not manage to gain any knowledge about outside world. And well, the one big reason why in classical physics we need trust is that information can be copied arbitrarily many times without being disturbed. And so in cryptographic scenarios especially, this is what forbids somehow trust-free classical communication. So in some sense, classical physics cannot pass this Cartesian doubt test. Well, but then with quantum physics, as probably all of us know, the things are a bit different. So quantum physics actually can work trust-free. And well, one big reason is that there is this no-cloning theorem. So in quantum physics, information exists as a unique, and making a copy necessarily destroys or disturbs the original. And well, no-cloning is also related to this principle of monogamy of quantum correlations that are also somehow in the core of many cryptographic protocols. Okay, so but then these quantum correlations, they have a classical footprint that is non-locality of measurement correlations that can serve us to ensure that somehow there was some quantum resource that we were using and that could help us to be sure that our communication channel is trusted. So in this sense, what we are trusting, so it's not that we are completely abandoning any trust. So we trust only these classical labels and we abandon any trust in quantum operations. And it still allows us to gain knowledge about underlying quantum properties, okay? And well, this is related to the first important topic that I want to tell you something a bit about it. It's Bell non-locality. So okay, so Bell non-locality, the roots reach to well to the golden time of quantum theory when like people could answer a lot of questions where classical physics did not have any. So quantum physics was giving answers where classical physics was stuck. So there was photoelectric effects and many other things. And then we had this famous reaction of Einstein and this famous paper with Podolsky and Rosen. And then, well, there is this, many times we hear that, okay, did he understand well quantum theory? Or, I mean, if this article there says that he attacked quantum theory. So, well, indeed, like yes, like Einstein profoundly understood the quantum theory because in this paper he actually pointed out to something that that will many decades later give us tools to do all that we are doing now. So he posed a very good question, but we needed to wait a lot of time to get an answer. So the problem that he pointed out to was that, okay, so here it seems that something is missing. Yeah, but local measurements on pure states are random. So like Einstein didn't have a problem with this apparent randomness if we didn't characterize some state well, and then okay, it's fine if we have a random result. But the problem is if we have a perfectly pure system, we have all information about the system, it is described by some pure states, and then we make some measurements, and then they are random. So he had a problem with this, and they made this postulate of existence of these local hidden variables that would remove this apparent randomness. Okay, and then the answer to this, formalization of this thing came some 30 years ago with famous Bell theorem. So, well, Bell wanted to see, okay, what can we tell about some theory that allows for existence of local hidden variables? So let's imagine that there are these local hidden variables. So what would be the consequences? And in his theorem, he found that local hidden variables bound the strength of measurement correlations between distant parties in all generalized probabilistic theories. So he was not talking only about quantum theory or anything. Like he said, okay, let's take a theory. It allows for existence of local hidden variable models. What is happening? So there will be a bound on the measurement correlations. So yeah, in principle, this hidden variable that would impose this bound is usually called lambda. And then, like the standard scenario where we think about these things is this Bell scenario, where we have like somehow in two laboratories, two agents. So there is Alice with her device that she just looks at the input X and output A. And Bob has his device also. He makes a measurement denoted by Y. He gets output B. well, and then they get so they repeat their experiment many times, and they get their correlation probabilities, P, A, B given X, Y. So then if there is some lambda that is governing these outputs, simply because of causal structure of this system, these correlation probabilities will decompose in local way. So there is simply this hidden variable lambda, and then output A of Alice will depend only on value of hidden variable and her input, and for Bob the same way. Okay, so then, okay, what happens further is that, well, as I said, this correlation probability is decomposed in a local way, and indeed, like all the probability distribution allowing for such a local decomposition form a polytope, and then, well, if we see this polytope, then such probability distribution satisfy inequalities determined by various hyperplanes that are bounding the local polytope. So somehow, like the strength of these correlations is determined by Bell inequality, and well, Bell inequality is simply a function of probability distribution. So it has some form like this, and for all theories that admit existence of local hidden variables, like the bound will be some beta that is called local bound. So here is how it looks like geometrically. And then violation of Bell inequality implies that the underlying theory is incompatible with hidden variable models. And then, well, I mean, there is a bit of mess about the terminology there, but okay, you can decide how you want to call it. And the interesting thing, of course, that we all know is that quantum theory allows for violation of Bell inequalities. And, well, there is, I suppose that many of you know, but maybe not everybody. So I give just some very simple example. The simplest Bell inequality is CHSH inequality. So in that case, we have two parties. So we have Alice and Bob. And Alice has input that can take two possible values, and Bob the same. And their outputs also can take one of two different values. And then, well, Alice's measurement observables can be described by A0 and A1, Bob's B0 and B1. They have this shared state. And, well, then we take into account this correlator that already Nicolas defined in his presentation. So, yeah, and then for this correlator, we have one rule that will tell us if Alice and Bob perform different measurements and they have state, what will be the value of the correlator. And, well, the CHSH inequality, it has just these four terms, and local bound is 2. Now, if the state they share is maximally entangled pair of qubits, and if Alice and Bob's measurement observables are anti-commuting, so here you can see in the block sphere how they look like, then one can calculate that the value of CHSH inequality will be this magical number for non-locality to square root of 2. Okay, so then simply looking at this local decomposition for correlation probabilities, we can see that there are two necessary ingredients for Bell non-locality. So we can see that all separable states lead to locally decomposable probability distribution, which means that if you want to see violation of Bell inequality, the shared state must be entangled. And then there is also the constraint on the measurements that all parties apply. So the measurements cannot be jointly measurable, so they have to be incompatible. Okay, and then somehow if we see by violation of Bell inequalities, we see that the state, we know that the state must have been entangled and the measurements were incompatible, or they could not be jointly measurable in different way, said. And this somehow, well, we knew this long time ago, but then it led to emergence of this device-independent paradigm. So only by observing Bell violation, we know that there was entanglement and incompatibility in our system. And, well, this witness is based only on observed probability distribution, P, A, B given X, Y. So we don't need to know if we had the photons or some other system, or we don't know in which degrees of freedom, like anything was encoding. So we just look at X, Y, A, B. We find these frequencies, and then if it violates Bell inequality, we know that there is entanglement, and we know something also about the measurements. So there is no trust whatsoever in any of the devices used in the experiment. So there we come back to this Cartesian methodological doubt that we could also place here, and still we could learn something. And, well, this form of witnessing, where we are making our conclusion only from looking at the probability distribution, is called device independent, and, well, now already for some I don't know, 15 years, it is or 10, I don't know how many. It is quite active field of research. So, well, saying this, we could say that, well, Bell inequality violation is the basic device-independent, or its basis for basic device-independent protocol. So just observing violation, we know that there is entanglement and incompatibility, we can witness something. But then self-testing will be another, well, let's say, basis for more device-independent protocols. So I will tell you two ways how we could look at self-testing, what it is. So in simply theoretical way, and well, I will hear in the rest of the paper and the conclusion that come from our results would be mostly applied to this first way I'm talking about self-testing. So some of the ideas is, can we find something that is reverse to Born rule? So I mean, Born rule provides us a way to calculate correlation probabilities if we know the states and measurements. So we know what states Alice and Bob share, what measurements they are applying, and we can easily find what are the expected correlation probabilities. But then, okay, now we already talked about this device-independent paradigm. We already talked that, okay, we have our experiment, we have these frequencies, P, A, B, X, Y, that can help us maybe to find also the ideal correlation probabilities. And then self-testing aims to find inverse relations. So it says, okay, let's assume that I have correlation probabilities, this theoretical concept of correlation probabilities. In which cases can I ever, or in which cases I can from that infer something about what was the state or what were the measurements. So in that sense, it is trying to find some rule inverse to Born. And in this sense, and that is the sense that well, self-testing will be used here in this in our work, is that self-testing can be seen as some map between the set of measurement correlations and quantum experiments. Well, what kind of map we have to see. And then there is this other way of thinking about self-testing, and it is actually like device-independent certification of quantum states. Because if we imagine an experiment, we would do like, we would find our frequencies, we could try to estimate what are the correlation probabilities, and then we could say in principle, okay, that was my state, and those were my measurements. But then, well, we have a question just, okay, how can we actually, what are the assumptions that we are making? Is our source IID, like what we do with finite statistics and things? So like somehow to actually be able to interpret self-testing as device-independent certification of quantum states, we need to do several more steps that are highly non-trivial. Okay. So, but yeah, in principle, like I said before, that somehow like the simply Bell inequality violation can be seen as a basis for device-independent witnessing of entanglement and incompatibility, and there were experiments about this. But then if I don't think about just Bell violation, I think about maximal Bell violation, like then it can be seen as a device-independent witness of particular quantum states and measurements. So this is kind of the aim. We can see if it is possible or not. So somehow I would say that, yes, self-testing can indicate us to quantum state and measurements certification protocol. So, or at least, well, in some sense, it could say also what states and measurements we cannot device independently certify. We can never hope. If there is no self-testing for them, then the story is done. If there is, then we can talk. Okay. So now, well, there is just some terminology and formulation of the problem. So, like in principle, we have experiment that is involving untrusted source and untrusted measurement devices. So, well, there is this picture that I showed many times. And so I will not involve many equations, but in principle, I will denote with prime values what is physical. So this is what is in principle in our lab. So like the shared state would be this psi prime, or I will sometimes use rho prime. And then the measurements will be m prime and for Alice and for Bob. And so this is the experiment that is in the lab that I will call physical experiment, and the state I will call physical state, and measurements I will call physical measurements. Okay. And then, okay, since we are here in device-independent scenario, we can add, we can increase the Hilbert space as we want because we don't make any assumption about the dimension. We can consider the purification of our state, and we could also consider with some also caveats also, but we could consider extension of measurements and consider them projective. So this somehow many times allows us to make simpler calculation in self-testing. And then on the other side, we have ideal experiment that is involving what is the specification of the source and measurements, and these I will call reference experiments. So, and I will denote them without primes, so just psi, m, and m, ma given x and b given y. Okay, so somehow this reference experiment is the blueprint. So if we get some source and some measurements, and somebody tells us this source produces this state and measurements are doing this, we'll say, okay, that is reference. But what is actually there, we don't trust. We'll call it physical. So aim of self-testing is to find relation between the physical and reference experiment. In the ideal case, we would like to say that, okay, they are the same, or they are in some sense equivalent. We'll see how. But also self-testing can go further and not need to make perfect equivalence, but find some relation between them, let's say. Okay, so now it's exactly the question, okay, what can we do or what cannot we do? So for example, in some device-independent scenario that is, let's say, multipartite, we have this state and we make some measurements and get outputs. Okay, so if this is if here I described in schematic way the reference experiment, when there are some transformations that somehow can be done that would not affect our probability distributions. So for example, if I change in a systematic way, so I change the basis for this particle, and then I change also I do rotation of measurement, and I do some different rotation for different particle and different measurement. So this will not change probability distributions. I will make this more technical in the next slide. This is just schematic. And then there is also something that we could relate to handedness or complex conjugation. So somehow if I do complex conjugation of measurements and complex conjugation of state, these correlation probabilities are inner product, and inner products will not change if I do this complex conjugation. So here you could see just that I change this handedness. Here it is somehow right, and here everything is left. And this will also, I cannot see this in a device-independent scenario.
What's A? A is just the basic experiment, or?
Well, this is just a scheme for arbitrary device-independent experiment. Yeah, it's this part is relevant, let's say. Okay, so now just to make it a bit more technical, so yeah, as I already showed a bit schematically, like the situation is not that simple when we are trying to exactly identify quantum system in a device-independent manner. Okay, so there is a whole class of state and measurement transformations which leave the probability distribution invariant, and well, one is local change of basis. So you see here, if I just rotate measurements and I accordingly rotate the state, it will produce the same correlation probabilities as if I didn't do it. So somehow, like, for example, if I have a maximally entangled pair of qubits, psi plus, all other free bell pairs will be, for me in a device-independent scenario, the same thing. So this is kind of equivalence class. Then I also might have these uncorrelated degrees of freedom to which measurements act trivially. So I might have my state, that is ideal state, and then I add something on top of it, and my measurements act trivially on it. So they don't contribute to these correlation probabilities at all. So these things would also be, to me, in my experiment, the same thing. And then the thing is that I could do, on the top of, I could do first, I could append these additional degrees of freedom, then do again this local unitary, and on and on and on. So like these two things I could do repeatedly, and this kind of transformation are encompassed by the notion of local isometries. So in principle for me, okay, so here there is prime missing, but I want to somehow show that under action of local isometries, my physical and reference experiment are the same. And also from the other part of my schematic representation, so on this first slide I showed you some things that are physical, that we can physically do, but then there is this problem of complex conjugations. And as I said, simultaneous complex conjugation of state and measurements, this does not change the correlation probabilities, but this is not a physical operation, so this is something a bit problematic. And if we say that some reference state that I want to self-test is complex, its complex conjugate will be this psi with star. And then, well, it could happen in multipartite scenario that these two states, if I do complex conjugate, that it is not locally unitarily equivalent that these two states are not locally unitarily equivalent. So, for example, if I have maximum entangled pair of qubits, I do complex conjugation, nothing happens. But already for the states of free parties, it was shown that there are states, I do complex conjugation and I get different state. Not obtained from the first one by making just rotations of bases. So these are somehow different realities. Okay, but then these states give rise to the same correlation probabilities, and best we can hope from our self-testing result is to bring the physical state to coherently controlled superposition of reference state and its complex conjugate. So this is something like I wrote it here. So our isometry will bring my psi prime to psi tensor some junk, plus psi star tensor some other junk. These two junks should be normalized well, and they should be, of course, orthogonal. So okay, the thing is that, I mean, yeah, in principle we could imagine implementation of this, that I could prepare this in a lab, and I could make measurements also like coherently do like the ideal measurements or complex, and well, it will, so I cannot escape this. Okay, and then just let's return, because we already, I already showed that CHSH inequality is, well, it demonstrates the non-locality of quantum theory. And now, it is also related to self-testing as the simplest self-test that we have. So maximal evaluation of the CHSH inequality implies that Alice's and Bob's measurement anti-commute. And then in some sense, anti-commuting pair of operators defines a qubit subspace. And once we can extract this qubit subspace with the help of these anti-commuting operators from Alice and Bob, we could use the measurement correlations and conclude that the state they share must be maximally entangled. So this is something that was understood by Werner first in '89 and Popescu in '90 and Cyrelson, but then in the context of self-testing later in 2004, 5th, and I don't know. So this is somehow maximal CHSH violation is the simplest self-test. And then, well, the question is, how far can we go? What else do we know about this self-testing? So, I mean, after this first self-test, people were doing different things. So people understood how to self-test all partially entangled pair of qubits, then all qubit pure bipartite entangled states, all qubit graph states, all qubit GHZ states, all decay state. And then the question is somehow, okay, we could just go and take one state and see, okay, I can self-test this, I can self-test that, but okay, it's somehow as an open question or proof of principle is, okay, so can we self-test any pure entangled state? Is there something that forbids me this, or I can do this, and somehow if I can do this, it somehow indicates to some kind of device-independent formulation of quantum theory. So this is the question that we somehow were thinking about. And well, as I say, so somehow all solutions up to now are tailored for a specific state or group of states sharing some particular symmetry. And it is very difficult to find general method for all possible entangled states, since, okay, anybody who was working a little bit with multipartite entangled states knows that their structure is really a mess, and it's very complicated. So for qubit states, we have some ideas how to do it, and I think that somehow some general method can be approached. But for qubit multipartite states, like that is really problematic part that remains highly problematic, and I'm not optimistic that soon we can find some very general solution in this standard Bell scenario to self-test all of them. But okay, we have some way how to do it if we change the game a little bit. Okay, so I will make some intermezzo with quantum state teleportation. So I think all of you know well quantum state teleportation protocol. So we have Alice, she has some state, phi, and then she shares with Bob EPR pair. She makes Bell state measurement, and then depending on the outcome of her Bell state measurements, she teleports to Bob the state up to some local unitary. So, well, this is a quantum teleportation is one of the basic quantum information protocols used for repeaters, for many things. And then here I will just look at a bit of different view of the protocol that will help us with our self-testing trouble. So I have exactly the same situation that I had before, but I just added that Bob applies some measurement here. And then I want to look at this thing as the measurement is teleported to this state, and this is indeed the case. So somehow if I look at probability to get output, A is output of Bell state measurement, and B is the output of Bob's measurement, so it is just trace of, well, Bell state measurement, Bob measurement, and then this state Alice has and the state they share. Well, and then there is just the thing that, okay, this measurement, if we want really to somehow apply it to this state, must be, depends on the outcome of Bell state measurement. So we have to rotate it depending on what is obtained here. And taking into account this correlation, well, we could basically, by doing this kind of small transformation, we could, in this since somehow Bob can effectively make measurement on the state that is not with him but with Alice. Okay, so this is very important because it will help us a lot to solve some troubles in other device-independent protocols. So, for example, well, I will now just give a different view than is standardly given about these things about device-independent entanglement detection. So, if we want to detect entanglement in a device-independent manner, so we want to look for a violation of Bell inequality. We see violation of Bell inequality, we have entanglement, but then the problem is that well, only entangled states can violate Bell inequalities, but there are some entangled states, weakly entangled, that do not violate any Bell inequalities. So in this scenario here, where I have just black boxes, there are some entangled states that will escape, and I will never be able to confirm that they are entangled. So somehow, well, it was somehow assumed that, yeah, there is it's the end of story. In a device-independent scenario, we cannot detect all entanglement. But then there is something called teleportation-assisted device-independent entanglement detection. So basically, you could see it here that, okay, in principle, in a device-dependent way, so that is what we do standardly when we make entanglement witness, for example. Well, entanglement can be witnessed for any entangled state. So for every entangled state, there is a witness that I measure. If I have tomographically complete set of measurements, I can do any entanglement witness, and everything is fine. So this would be in case I have this kind of picture here. But then, if I use teleportation, well, any witness can be performed with the aid of additional maximal entangled pair of qubits. So, for example, if this is part of some entangled state that I want to witness device independently, but I cannot because it is weakly, I could then somehow, the problem is that, well, when I apply a measurement on it, it will give local statistics. But if I do it teleportation assisted, so if this party shares with some other party maximally entangled state, and I apply to that measurement remotely, I could self-test that measurement. And then I return myself to basically device-dependent scenario. Because if I apply it directly to the state, I cannot self-test it. It is weakly entangled state. It is not pure. I cannot do it. But since it is applied originally on phi plus state that is maximally entangled, I could do self-test of that. I could self-test the measurement, and I'm somehow returned to device-dependent scenario where I could do then basically perform any entanglement witness. Okay, so well, this is somehow this concept that, okay, if I have some multipartite entangled states.
Sorry.
Yep.
Okay, can you go back to
yep.
So what's the punchline here? That if you have more parties, then you can do self-testing for even weakly entangled.
Yes, exactly. Not self-testing, but just entanglement detection. So you can see it here on this. Okay, for example, I will just miss part, but okay, in principle, if I want to look at entanglement detection for some device independent for some state, I will do it in this scenario. But then for some weakly entangled states, I cannot do it. But then here, if I add so in two-party scenario, I add two more parties, and then my parties share with them maximal entangled states, then I could self-test measurements that these auxiliary parties apply, okay. And then, when I self-test them, when Alice applies Bell state measurement and Bob applies Bell state measurement, I am teleporting those measurements to their systems, but now I know what they are. While in this case, if I apply them directly, device independently, I don't know. So here, somehow self-testing helped me to do device-independent tomography, basically. But the price is that I have additional Bell pairs, okay? So somehow the protocol would be that, yeah, so somehow Alice and Bob, in some rounds of this protocol, they would be asked to do measurements that would allow to self-test this maximum entangled state, and then measurements of Charlie and here Daisy. And in some rounds, they would be asked to do a Bell state measurement. But since these two auxiliary parties don't know what these main parties are doing, they must be somehow doing the same thing all the time. Because in some rounds, they are doing the test, self-test. In some rounds, they are doing entanglement detection. Since they don't know which round is testing and which round is entanglement detection, so they do always the same thing. And that way, somehow, the self-testing of just the simplest self-testing of maximal entangled states allows me to achieve something that in standard bipartite Bell scenario I was not able to do. Okay. So yeah, here is just one thing that is important. That well, to do this, I need to self-test tomographically complete set of measurements. And well, as I said before, CHSH inequality can certify 2 anti-commuting measurements per party. But if I make 3 different CHSH inequalities, then it allows me to find 3 mutually anti-commuting observables, and then I could self-test them to be 3 Paulis. And if I have 3 Paulis, that is tomographically complete, and then I can do whatever I want. So this is kind of the basis part, basic self-testing part for this kind of teleportation-assisted protocols, okay? So now I told you this in a way through this teleportation-assisted paradigm, but it was actually done in a bit different way. It was done through quantum input paradigm. So if I don't have classical Bell scenarios, but I have quantum inputs, so I have, instead of classical inputs x and y, Alice and Bob are receiving quantum state psi x and psi y, and they are perfectly characterized. And then these parties apply joint measurements on the input state and the part of the state they share. And then the correlation probabilities are obtained in this way that you see here. But then, so here these psi x and psi y are trusted. And then I could see these probabilities as basically applying, well, measuring, probing this thing m tilde with these quantum inputs. And this m tilde is somehow shared state that is then transformed to Hilbert space of psi x and psi y by these joint measurements MA and MB. So in principle, I could do tomography of this effective measurement m tilde. And then, well, from the form of this, if I do tomography of it, from the form of this effective measurement, I could learn something about the state. So if this is entangled, then means that this state must have been entangled. If it is pure, then it must mean that this state was pure, and that also helps me to do self-testing with quantum inputs. So in some previous paper with people from ICFO, we were using this paradigm basically to show that any quantum state, any quantum entangled pure state can be self-tested if instead of classical inputs, I have quantum inputs. Okay. So this was a kind of this intermezzo towards our main result. And, well, so somehow, just from this thing that I said previously, I mean, it hints a bit what is the solution to our problem. So, well, we know that tomography certifies all the states. If I have tomographically complete set of measurements, I apply them to my multipartite states, I could certify any state. It doesn't need to be pure or anything. So I just see this correlation probabilities. I know what my measurements were, and I can retrieve the state, okay? And, well, but now the thing is that, well, in device-independent scenario, I cannot have trusted measurements. This is not device-independent, but I can use my trick with teleportation of this measurement, where I am physically applying measurement to a part of EPR pair, but it is teleported to some remote state. And we can use these 3 CHSH inequalities to self-test the tomographically complete set of inputs here, set of measurements here. Okay. So then, how it goes in principle. So, well, we have this, we have tomography that allows us to retrieve any possible state. And then here, instead of doing that, because we cannot, we don't have such a resource, so then we'll have additional parties. So like these here that I show are my main parties that share some state that I want to self-test. And then each of them is sharing a maximally entangled pair with some auxiliary party. And by using that additional maximally entangled pairs, I could self-test any measurements that are applied by the auxiliary parties. But then, if these main parties perform Bell state measurements, these self-tested measurements are teleported directly to the state I want to certify. So this is basically the same principle as for this device-independent entanglement detection. But here, the missing part that we needed was this well, self-testing of all states with use of quantum inputs. And then, okay, so we did the proof in 2 scenarios. So, well, in principle, device-independent scenario does not make any assumptions about our experiment ideally. But then sometimes we could say, okay, I mean, since we we have some network. So network would be that I have my state that I want to self-test, and then I have these additional maximal entangled states. And then I could assume that they are independent. I just have this network structure, and I say, okay, I will live with this assumption. Or I might say that, okay, I don't want to assume any independence. I will think that my state is shared by all possible parties. So in this scenario, when network structure is assumed, well, apart from n parties sharing the state to be self-tested, there is one auxiliary party, and all n parties are sharing one maximal entangled pair with this one additional auxiliary party. And then the physical state, so this is what I assume is there, has this structure, has this network structure. So I start with that. And well, my reference state would be like, as I said, n maximal entangled pairs and one state that I want to self-test. If I don't assume network structure, then, well, I have the same reference state. So I have my state to be self-tested, and I have n maximal entangled pairs. But now the physical state, I don't assume that it has any structure. It is just shared completely between all the parties. And in this scenario, apart from n parties that are sharing the state to be self-tested, I have n auxiliary parties. So in one scenario, I have 2 n parties. In the other one, I have n plus 1 parties. Okay. And then, well, the proofs are similar, but, well, basically doing the same thing, but somehow the technique of proof is different. So I will just give here some short outlook. And so if I don't have network structure, so I have this multipartite, all big states. So in that case, so measurements performed by auxiliary party can be self-tested up to complex conjugation. So, for example, in this scenario, I could self-test all these red measurements, okay? And then all main parties apply Bell state measurements that are not trusted, but if they do it, I can do the self-testing. And, well, then the states shared among main parties is sent through a teleportation channel to the auxiliary parties. So when all the main parties do the Bell state measurements, this state is teleported to the auxiliary parties. And since I self-tested measurements of the auxiliary parties, I do tomography, and it's all fine. But so somehow here, the isometry that I was all the time talking about is somehow sending state of the main parties to some ancillary states of the auxiliary parties, ancillary space. In the network structures, so somehow there, again, so somehow measurements performed by my auxiliary party can be self-tested up to this complex conjugation always. And in that case, like what I see is that when these auxiliary parties apply this, make this measurement on maximal entangled states, so we self-test that, and by doing that, they basically prepare they steer states of main parties to some state they want that can be treated as quantum input. And since we already before said that in the scenario with quantum inputs, I could self-test everything, then I could use my results from self-testing with quantum inputs and basically self-test my state. But, okay, so these are somehow just different ways, because in one way I am going from main parties and I'm teleporting the state. In the other occasion, I am self-testing quantum inputs, and so I'm just looking in one way from main to auxiliary, and the other way from auxiliary to main. But the important thing is that if I assume network scenario, I can do something that if I don't do it, cannot do. So I told you before that in standard self-testing, we cannot exclude that I have this coherent this coherent controlled superposition of state and its complex conjugate. If I assume network scenario, I know that it is one or the other. So I will not know if it is state or its complex conjugate, but I know that it is not this their superposition, but it's one or the other. And this is something that in standard self-testing we cannot do. If I don't make this network scenario, I don't assume this independent of sources, and I don't consider network scenario, then I can do the standard thing. So for every multipartite entangled state, I can find isometry that maps it to superposition of reference state and its complex conjugate. And, well, this is somehow basically for qubits closing this question of, well, what states we can certify in the device independent way, or what states we can self-test. But the thing is that, yeah, we need additional resources. We need all these maximum entangled pairs of qubits. And with help of that, we could find our answer to our problem. So, well, now going beyond qubits is very technical, but I will just give one idea, and that is that, so somehow if local dimension of the reference state is bigger than 2, well, we can always embed the state in a Hilbert space of local dimension 2 to the m, where m is log 2 of d, and that is a state of m qubits. And then, well, the whole procedure given for qubits can be mapped to situation where I have qubits that I see of as many pairs of qubits, okay? So to achieve that, we use the method of parallel self-testing. So somehow, like, this is also one field of self-testing where people were working, but for example, if I can do self-test of some state, then I could do also self-test of a situation where I have tensor product of these states. And then if I have tensor product of these states, it is state of larger dimension, and so for large m, I could embed in that any state that I actually need. And well, with the results from parallel self-testing, we could just somehow add up all these steps, and we can make our procedure work for, well, arbitrary pure entangled state with any local dimension. Okay, so for open question, well, one is that, okay, we pose this question, okay, can we self-test all the states? And well, we give this paper and say, okay, we self-test all the states. But then many people would be complaining and say, okay, but okay, this is not exactly the answer to the problem, because you demand that you have these n EPR pairs, so this is not the answer to the original question. I mean, you do you do self-testing of your state and n EPR pairs. So the question, if we can do it in the standard Bell scenario, where we don't need other resources, that still remains an open question. And well, it would be interesting to understand if we can, or well, it would be, I don't know, it would be very surprising if we would understand that we cannot, especially given this, this result that we have now. And then, well, the other thing that, that is interesting is, okay, because this is really a proof of principle result, because I need, well, okay, if I want to apply this experimentally, I need these entangled pairs that, okay, this is maximal entangled pairs, this is not a big problem, but I need a Bell state, full Bell state measurement. And this is somehow a very problematic thing to do. So when we were making first draft, like one colleague wrote like, okay, we need several maximal entangled pair of qubits and Bell state measurements that are things readily applied in labs. And I was like, okay, no, we cannot do this. But then my question is, and I somehow think that it should be possible if I have just partial Bell state measurement. And if I concentrate on that output and I get something that looks like my state for when I post-process, can I conclude anything? And well, this would be an interesting thing, but one would need to change quite a bit perspective because, like, well, I would not have any more isometries or like, because I would be working with just post-processing on one output. But I'm somehow hopeful that maybe this actually could be done. So yeah, these are somehow the two big questions for me that remain after this. And well, I have quite some time more, so that would be all for me.